What specific problem does AlphaGeometry2, AG2, aim to solve, and how does it differ from its predecessor, AG1, in addressing this issue?
AlphaGeometry2, AG2, aims to solve the limitations of its predecessor, AlphaGeometry, AG1, particularly in the domain of geometry problem solving for the International Mathematical Olympiad, IMO. While AG1 achieved a 54% solve rate on IMO geometry problems, it was constrained by a limited domain-specific language, an inefficient symbolic engine, and the capacity of its language model. AG2 addresses these issues by introducing a more powerful Gemini-based language model, a faster and more robust symbolic engine with optimizations for handling double points, and an expanded domain language that includes additional geometric concepts such as locus theorems and linear equations. As a result, AG2 significantly improves performance, achieving an 84% solve rate on all 2000 to 2024 IMO geometry problems, thereby surpassing the average gold medalist.
Can you describe how AlphaGeometry2, AG2, works step by step, including details about the language model, symbolic engine, and search algorithm?
AlphaGeometry2, AG2, operates through a multifaceted approach that integrates a powerful language model, an advanced symbolic engine, and a novel search algorithm. First, AG2 utilizes a Gemini-based language model that has been trained on a larger and more diverse dataset, allowing it to understand and formalize geometry problems from natural language into a domain-specific language. This formalization process is automated, with Gemini translating problems and generating auxiliary constructions necessary for solving them. Next, the symbolic engine, known as DDAR, Deductive Database Arithmetic Reasoning, has been significantly enhanced to handle more complex deductions, including the ability to manage double points and execute faster algorithms implemented in C++. This engine computes the deduction closure, iteratively adding new facts until no more can be deduced, which is crucial for the proof search process. Finally, AG2 employs a novel search algorithm called Shared Knowledge Ensemble of Search Trees, SKEST, which runs multiple beam searches in parallel. Each search tree attempts to construct solutions using auxiliary points generated by the language model, while also sharing successful deductions across trees to improve efficiency. This collaborative approach allows AG2 to explore a broader search space and significantly increases its solve rate on IMO geometry problems.
Could you provide a simple illustrative example of how the AG2 algorithm processes a specific geometry problem, explaining each step and the role of the different components involved?
To illustrate how the AG2 algorithm processes a geometry problem, consider a problem like given a triangle, ABC, with two equal sides, AB equals AC, prove that angles B and C are equal. The first step involves the automated formalization where the natural language problem is translated into the AlphaGeometry language using the Gemini model, resulting in a structured representation like triangle ABC, AB equals AC, ekangle BABC CBCA. Next, the novel search algorithm, Shared Knowledge Ensemble of Search Trees, SKEST, initiates multiple parallel search trees, each attempting to construct auxiliary points and run the symbolic engine, DDAR, to prove the goal. During this process, the symbolic engine applies deduction rules to derive new facts from the initial premises, leveraging its enhanced capabilities to handle complex constructions and double points. Finally, if the symbolic engine succeeds in proving the equality of angles, B and C, the solution is confirmed, showcasing AG2's ability to solve the problem efficiently through its integrated components.
What are the practical benefits of using AG2 over previous methods for solving geometry problems, and how do these benefits contribute to its improved solve rate?
The practical benefits of using AlphaGeometry2, AG2 over previous methods, such as AG1, include a significantly enhanced language model, a more robust symbolic engine, and an advanced search algorithm. The Gemini-based language model in AG2 is trained on a larger and more diverse dataset, which allows it to better understand and generate solutions for a wider range of geometric concepts, including locus theorems and linear equations. Additionally, the new symbolic engine, DDAR2, is optimized for speed and efficiency, enabling faster deduction closure and improved handling of complex geometric scenarios, such as double points. The novel search algorithm, Shared Knowledge Ensemble of Search Trees, SKEST, allows for parallel exploration of multiple search trees, facilitating knowledge sharing and accelerating the proof search process. Collectively, these enhancements contribute to AG2's impressive 84% solve rate on all 2000 to 2024 EMO geometry problems, surpassing the average gold medalist, and demonstrating a significant leap in AI's capability to tackle challenging mathematical reasoning tasks.
How does the validation process for AG2 work, including the datasets used, the benchmarks for performance evaluation, and how the results substantiate its effectiveness?
The validation process for AlphaGeometry2, AG2, involves evaluating its performance on a set of geometry problems from the International Mathematical Olympiad, EMO, spanning from 2000 to 2024, specifically translating these into 50 AlphaGeometry problems, referred to as EMO AG 50. The main benchmark for performance evaluation is the solve rate, where AG2 successfully solves 42 out of 50 problems, surpassing the average gold medalist for the first time. Additionally, AG2 is tested on a new set of 30 hardest EMO shortlist problems, which have never appeared at the EMO, further demonstrating its capabilities. The results indicate a significant improvement in problem-solving ability, as AG2 achieves an 84% solve rate on all 2000 to 2024 EMO geometry problems, compared to the 54% solve rate of its predecessor, AG1. This substantial leap in performance is supported by the enhancements made in AG2, including a more powerful language model, an advanced search algorithm, and a stronger symbolic engine, all contributing to its effectiveness in tackling complex mathematical reasoning tasks.
What limitations does AG2 have, particularly regarding certain types of geometry problems, and how might these limitations influence future research directions?
AG2 has notable limitations in addressing certain types of geometry problems, specifically those involving inequalities, variable numbers of points, and advanced techniques such as inversion, projective geometry, or radical axis. These unformalizable problems account for a portion of the unsolved EMO problems, indicating that AG2's language does not currently encompass these complex scenarios. Additionally, while AG2 achieves an impressive solve rate of 84%, it still struggles with problems that require advanced geometric reasoning techniques, which are not implemented in its current symbolic engine, DDAR. This limitation suggests that future research may need to focus on expanding the language model to include these advanced techniques and enhancing the symbolic engine to handle a broader range of geometric concepts. Consequently, addressing these gaps could significantly improve AG2's performance on a wider array of geometry problems in future iterations.